Let's complete the circuit analysis for this simple series circuit. So it is a series circuit because there are only series connections between the two resistors. The two resistors are in series with each other and they're in series with the battery. I've drawn a very neat diagram and with a ruler, and I've labeled the positive and negative terminals of the battery. I've labeled conventional current, which is what we're using in this course. Although I have to admit the most important time that you remember that is once we get to the right-hand rules in the next video. So for circuit analysis, I strongly recommend that you draw a neat table organizing the V, I, and R for each of the components of the circuit. And this will do a couple of things. It will help keep your work, it will establish what your final answers are. It will help organize your givens. And if you ever get stuck, there's a strategy for moving forward. So moving forward, the goal of circuit analysis is to fill in all of these blank spots. And working horizontally, the relationship between V, I, and R at any point in the circuit is Ohm's law. Vertically, the relationship is KVL, KCL, or a custom equivalent resistance formula. So what I do is you're gonna determine the number of rows is based on the number of resistors plus one, because you have one row for each resistor, or each light bulb, each resistor, each motor, whatever the load is. So I guess one for each load plus one for the source. So we have a 3-row table for this particular circuit. And if the circuit got more complicated, we'd just keep adding rows. So I filled in the givens, and I usually do that in pen. I draw the table with a ruler in pen. I draw everything that's given in pen so that I'm filling in my intermediate answers in pencil. And worst case scenario, if I have to just start the whole thing over again, I can take an eraser to the whole thing. And then the givens, I don't have to fill in. So in this case, I would observe horizontally, I can't move forward with Ohm's law for any row because I don't have 2 out of the 3 for any row. But vertically, I have all the resistances except for our equivalent resistance of the whole circuit. So my first step will be equivalent resistance. So for each step, you're gonna write a number and caption it, and then you're gonna write the math. And this is the most organized way to do it. This is gonna really help you check your own work and help others understand your work. So for equivalent resistance, we have R in series is equal to, in this case, R1 and R2 are connected in series, so it's R1 plus R2, 5 ohms plus 7 ohms. Gives us 12 ohms. So now I've done this either like in a color or pencil, and then that same color or pencil, I'm going to fill it in for a final answer of 2 sig figs. So I'm locking in my sig figs in this table. Actually, while we're talking about communication marks, the header of every table should indicate the units so that you don't have to repeat those units throughout the whole, for every entry in the table. Okay, now that we have equivalent resistance, now that we solved for equivalent resistance of the entire circuit, that's if all of the resistors were replaced by 1. Now I have 2 out of the 3 of the first row. So now for my second move, I'm going to use Ohm's law to solve for the current through the source. So we have V equals IR, and since we're talking about the source, it's the voltage gain across the source equals the current through the source times, it's really the equivalent resistance, but if you call it R source, I will know what you mean. So I source is equal to V over R, which is 6 volts divided by 12 ohms, which is 0.5 amps. And if we report it with the proper number of significant figures, it will be 0.50. Okay, now scanning over the rows, there are no rows that we can move forward with Ohm's law. And we've already used our equivalent resistance tool. So KVL or KCL, can you see any opportunities to use KVL or KCL? Well, in KCL, when we're talking about there being no split, no junction, the current is just the same the whole way through. So for my third step, I'm going to solve for I2 and I1 using KCL. So the current to the source is equal to the current through 1, which is equal to the current through 2 because they are in series. And I don't even have to write numbers to that. You do have to record something to show your process work for that. So you can just fill down the column for current. And finally, our last step, the only thing that is left for us to do is to solve for these last two spots. Here, as with any last steps of a circuit analysis, you actually have choices. If you really like Ohm's law, you can solve for it using V equals IR. So just current times resistance gives you that value. So that's one choice. I'm going to choose to use KVL, which is working vertically through that column because we haven't done that yet. And just to show you one, oops, this is supposed to be not KCV, KCL. That's Kirchhoff's current law. So I'm going to say we're going to use KVL to get V1 and V2. So I know that in one electron path, so KVL is where we look at the electron path. The electron path is over here. So we go that way, then this way, then this way. Technically, the electron path is from the negative to the positive, but it doesn't really matter. The path is continuous, whether you use conventional current or the actual electron path. The math is the same. We've got V source equals V1 plus V2. Oh dear, we have V source, we don't have V1 or V2. So we actually are going to need Ohm's law to find V1, and then we're going to sub that in here. It's going to be a known. So V1 equals I1 R1. So current 1 is 0.5 amps. Resistance 1 is 5 ohms. So we get 2.5 volts. So now we have 2 out of the 3, and we can solve for V2. So now this is actually just solving for my V2. So in this last step, we're using Ohm's law and KVL to find the last two. V2 equals V source minus V1. So if this is what we're solving for, you rearrange to solve for that. I'm not sure, hopefully the contrast is good enough that you can see. This is a brand new marker, so it is very pointy. So 6 volts minus 2.5 volts is 3.5 volts. 1, 2, 3, 4, 5, 6. So 3.5 goes here and 2.5 goes here. Now, if you were to scan this solution, not only can you see the givens are in pen and the intermediate answers are all in pencil, you can scan over to see do you have the significant figures of your final answers in this table? And you can trace your work a lot better than if you just, in grade 9, you'd probably just dumped all the numbers into that and you didn't show your work. This might seem like a trivial example, but trust me, it gets more challenging from here. So baby steps. Example 1B, circuit analysis. Now this is a parallel circuit. It's a parallel circuit because all the connections are in parallel. There's a connection between resistance 1 and resistor 1 and resistor 2 that's in parallel with each other. They are in parallel with each other and in parallel with the battery. So this is a pure parallel circuit. I filled in my givens. Notice that I didn't care to write the details of the significant figures of the givens. The 5.0 I just wrote as 5. I don't care about significant figures of givens. I just care about the significant figures of the final answers. So notice that this table is exactly the same givens table as the previous question, but our answers are going to be different. Our mathematical statements are going to be different because the connections are different. Once again, though, vertically, we're going to use KVL, KCL, or equivalent resistance formulas, horizontally, Ohm's law. So the first step would be to fill out resistance, the equivalent resistance, since that's the property of electricity that we have the most information. So equivalent resistance. Now, in this case, we do not just add up the 5 and 7 ohms. They are not in series with each other. So the formula is 1 over R equivalent equals 1 over R1 plus 1 over R2. I sub in that 1 over 5 ohms plus 1 over 7 ohms, 1 over R on my calculator. Now I have this trick that I really don't want 1 over R. I want R. So I'm going to use my reciprocal button right away. So I'm going to write that as this. The reciprocal button is the same as taking the entire thing to the -1. So I really need you to try right now on your calculator to see if you get the same answer, which would be, I think I've just, okay, disaster averted. I thought I wrote the wrong givens. Okay, we're back. So resistance is, we're gonna do on our calculator 1 divided by 5 plus 1 divided by 7, and then we're gonna press the reciprocal button or do to the power of -1. So for the equivalent resistance, I get 2.9167 ohms. Now I do not get 0.3 something. So if you got 0.34, what you solved for in your calculator was 1 over resistance. Remember to take the reciprocal because the equation is 1 over. So for that number, when I'm putting it into my table, I am going to round it to 2 significant figures. And of course, I should have headers on my first row. I should have units on my header. I've rounded to 2 significant figures in the table, but if I need to carry forward a number, which I am saying this because we will, we are going to use all of these digits, or in fact, there are more digits on my calculator. I'm just going to use the answer button. So the second step, once again, is to work horizontally. So our second step is Ohm's law. Ohm's law to find I source. If V equals IR, then I equals V over R. 6 volts divided by, now I'm only writing 2.9 ohms because there's not enough room, but I'm going to use the answer button on my calculator. 6 divided by answer button is 2.05714 amps. Again, when I go to write it in my table, I'm going to round it to 2.1. However, I'm going to carry forward the full answer in case I need it. So applying KVL or KCL would probably be our next step because Ohm's law, we can't move forward. We don't have 2 out of the 3 for any rows. Vertically, KVL, KCL, those are our only options. So for KVL, it's pretty easy. For the third step, KVL tells us that V source is equal to V1, which is equal to V2 because it's just a simple parallel circuit there. And now, since I have these two to fill out, I have 2 out of the 3 of these rows, and I can use Ohm's law. So number 4, I'm going to use Ohm's law to find I1 and I2. So V equals IR. That means I equals V over R. So for I1, that is 6 volts divided by 5 ohms. And we get 1.2 amps. Now, the very last box, we have more than one option. Oh dear. Okay. We have more than one option for this last box. We could use Ohm's law horizontally, which is probably what I'm going to do based on the way that I already set up my work for it. Or I could look at this junction right here, 2.1 amps going in, and if there's 1.2 amps going one way, I do 2.1 minus 1.2 gives us 0.9. So I know my answer here is going to be 0.9. Let me see if Ohm's law gives me the same number. Six divided by 7 is equal to 0.85714, which this number of amps rounds to 0.86. So actually, when I did that subtraction just now, I should have done 2.05714 subtract 1.2. The 1.2 was exactly 1.2, but this number was 2.057. So I would get 0.86 there either way. So that is for I2. So if you have the opportunity to use colors, maybe pencil crayons, that's maybe one way to help you when you're looking back on this work. You can see this number you got from this work here. That's a nice thing that you can do if you want to at home to help trace your work and double check. And you're of course going to want to double check that everything in this table has 2 significant figures, because out of the givens you had 2 significant figures and you did use multiplication and division somewhere in these lines. And that's how you do circuit analysis if it's strictly series, as in 1A, or simply strictly parallel, as in the